This is a lecture in a series of lectures covering MOSFETs and the use of MOSFETs as switches and as controlled current sources for the purpose of creating logic gates, such as a logic inverter, and then analog amplifiers. In this lecture, I want to talk about biasing an amplifier stage. And the amplifier we're going to look at is the only one that we've really looked at. I've not named it before, but it is called the common source because the source is connected to the common or the ground. And so this should be very familiar, but what we haven't talked so much about is how do you bias up an amplifier of this nature. So this voltage at the drain is going to be the output, and the voltage at the input or at the gate is the input. Now we know that we need to bias the gate to a particular DC voltage in order to bias the drain current of the MOSFET to a particular DC current, which will then in turn bias the output voltage to a DC output voltage. But we've always assumed that that biasing can be supplied by the signal that is coming in to the amplifier. And ideally, you'd really like the amplifier itself to take care of the biasing, and then for the input signal, the signal that is needing to be amplified, we'd like for that signal to not have to worry about the biasing. So what I want to set up is a scenario where we have an input signal, ultimately an input signal that is going to be a pure AC signal, no DC offset. So let's say it has some magnitude Vm, and it's a sine omega t. Okay, so just a simple sinusoidal signal, but it's centered around 0. So if you apply this signal right to the input of your MOSFET gate, nothing's going to happen because this signal is small. Let's say Vm is small, and in fact we're going to assume that it's much, much less than the threshold voltage of the MOSFET. So we need to provide the bias voltage from some other source. Now one way we could bias this is to tie, let's see here, we could do a weighted sum of two voltages. Okay, I could have an R1 and an R2, and if we supplied this voltage, call this V1 and we'd call this V2, then the gate voltage here, VG, could be equal to a weighted sum of the two. Right? We'd have VG is equal to, just by superposition, we don't have to worry about the transistor circuit at all because there's no current that flows into the gate. So all we have is a voltage divider for V1 and a voltage divider for V2. So by inspection, I turn off, and using superposition, I turn off V2, and I can write that VG is equal to R2 over R1 plus R2 times V1. And then turning V2 on and V1 off, we have R1 over R1 plus R2 V2. So we can actually sum two different voltages into the net voltage at the gate. And I'm going to use that to construct the following circuit, which is just essentially what I've drawn, but to the left here, but I'm going to redraw it to look a little bit different, but it's the same topology. So we'll have R1, have R2, and I'm going to call this, this will be our Vn right here, Vn. And because we already have a voltage VDD, instead of using the voltage V1, I'm going to just tie R1 up to VDD. Okay, so now we can write an expression for VGS. VGS is equal to the weighted sum of VDD and VI. It'll be R1 over R1 plus R2 times VI plus R2 over R1 plus R2 times VDD. And now we know that to bias the amp, we need a capital VGS, right? So remember that if I were to plot the VGS versus horizontal versus VO horizontally or vertically, we'll have something that looks like this. Okay, and this is up at VDD, and we want to bias this somewhere in the transition region. We don't want to be too close to VDD up at the top, and we don't want to be too close to 0 volts down at the bottom. So this will be our capital VGS, our bias point, call it Q, right? And there'll be a bias voltage VO. So what we have in our weighted sum expression back here is we have VGS being a function of VI plus a function of VDD. And if we adjust R2 and R1 for a given VDD, we can actually produce a VGS. So this is how we'll proceed. Given a desired operating point, okay, in other words, VO, capital VO, is equal to some voltage, and let's say in this case it's going to be 1/2 of VDD. Suppose. Could be something different, but let's suppose that. Then find the required IDS to get that VO, then the required capital VGS to get that IDS, right? And finally, pick R1 and R2 such that R2 over R1 plus R2 VDD is equal to the desired VGS, the required VGS, okay? So even though let's say VDD was 10 volts, and let's say VGS was equal to 2.5 volts, then we would need this ratio to be 1/4, right? And so for it to be 1/4, we can see right here this could be of the form 1 over 1 plus 3, or in other words, we would need R2 to be equal to 3 times R1. And as long as you pick that ratio, it doesn't matter what the absolute value of R1 or R2 is, but as long as the ratio is 3, then you will have your bias voltage. Okay, so let's suppose we actually do that. So let R2 equal 3 R1. Then what do we have? We have VGS is equal to 3 R1 over R1 plus R2, so that's 3 over 3 plus 1. Notice I haven't even picked these values, but it's just the ratios that matter, times VI plus 1 over 3 plus 1 VDD. So we'll have 3/4 times VI plus 1/4 times VDD. Okay? So now, when I want to find out what the gain of the amplifier is, I would say the small signal gain VO divided by VI, all right, not VO divided by VGS. But now, if we think of the entire amplifier, from what goes in from the input source or the signal, input signal VI, to what comes out the other end, it's going to be the ratio of small signal VO to VI. This is going to be equal to VO over VGS times VGS over little vi. Okay, and this second term, VGS over VI, is what we found right here. It's going to be 3/4, or in general, it is R1 over R1 plus R2. So adding in this this weighted voltage summer at the input has an impact on the overall voltage gain, and you need to include that. But the benefit is that you're able now to supply the bias voltage to the gate, capital VGS, from your battery or your power supply source, VDD, rather than requiring that it comes from the input, your input signal, VI. Okay, so now we can continue to write this. We can say that we have R1 over R1 plus R2, and then if you recall, for this amplifier, the small signal gain from the gate to the drain is equal to minus, so I'll put a minus up front here, minus R drain times GM, the small signal transconductance of the MOSFET, which can be found as square root of 2 times K times the operating point current, ID or IDS. It's also equal to K times V, capital VGS minus V threshold. Okay, so either one of those. So what have we shown? We've shown that if I put in a zero offset signal into an amplifier, okay, here's my amplifier, this type of amplifier, then, and this is relative to, okay, this is ground here, VI, then what I have coming out will be, this is VDD, I will have it biased at half VDD because that's what I requested, but it'll oscillate around 1/2 VDD. And I did not have to supply the bias voltage to the gate from my input signal. It was provided internally using this set of resistors R1 and R2 and tying R1 up to VDD. The above described circuit is useful in being able to remove the requirements of a DC offset to the input signal that we're trying to amplify, but it still has some shortcomings that we'd like to further improve on. So one of those shortcomings is that if the input VI should have a DC offset, it will add to the offset or add to the bias voltage that is being established by R1 and R2 and the voltage VDD. And so we can actually change the operating point of the amplifier by inserting or adding an offset to the input voltage. And what we want to do now is consider how we might be able to avoid that problem or solve that problem so that the input can pass the signal that it wants to have amplified, but not be able to alter the bias point of the amplifier. So we want to use or consider the use of a decoupling capacitor. At the input. Okay. So our circuit's going to change just ever so slightly. We will have our two resistors, R1 and R2, and R1 still gets tied up to VDD as before. The difference is that R2 gets tied to ground, and instead we are going to attach or connect VN or a VI source through a capacitor. Okay, C1. And the value of this capacitance for the purposes of this analysis is infinite. Now that's not realistic, but the idea here is that this capacitance is very, very large. And here's the idea. So the assumption here is that you have not yet studied circuits that involve capacitors and inductors at length. So you may not know how to solve for what is the time response of the voltage across the capacitor and when it's placed into some network of resistors and sources. But I think that you can appreciate the behavior of a capacitor when it's under DC or constant conditions, right? The capacitor VI relationship is as follows. IC, the current flowing into the capacitor, is equal to C dVc dt. So the idea here is that if the voltage across the capacitor is, or if there's current flowing through the capacitor, then its voltage is going to change. And at some point, if the circuit reaches some equilibrium, some steady state value, and if everything that's driving that circuit are DC sources, then the current will stop flowing through that capacitor. If it doesn't, then the capacitor voltage is still changing. It's changing at a rate of IC over C. So what we can do here is when we do the bias analysis, okay, the DC bias analysis, okay, we turn off all AC signals, okay, leaving only DC signals on. Okay, so what we have here is we will have our resistor divider, our transistor, and this will be open. Right, I'm sorry, I should just ground that because that's off. We have a capacitor here. And so everything is, the only sources in this circuit at this point are the static VDD source. And so what will happen is, if you say initially this capacitor has a voltage of 0 volts across it, then the voltage at the gate would then be at 0 volts. And there would be a current flowing through R1 that would be equal to VDD minus 0 volts over R1. So current would flow in, and it would start charging that capacitor. And instead of thinking of the capacitor as being infinite, think of it just as being a large capacitor. And it's going to take maybe a long time, but eventually that capacitor will rise to a voltage where the current flowing through R1 is going to become very small. Or I should say the current flowing into the capacitor will be very small, because as the voltage on the capacitor rises, there will be a rising voltage across R2, and so current that is flowing down through R1 will, instead of flowing through the capacitor, will flow through R2, and at some point, although it might take infinite time theoretically, the current flowing through the capacitor will go to 0. Okay, there'll be no more current flowing through the capacitor, and that will occur when the voltage at the gate will be equal to the voltage of R2 over R1 plus R2 times VDD, what we found to be the contribution of VDD to VGS in our previous setup. So under DC conditions, the capacitor is an open circuit. And then if there are any AC signals, the capacitor can be treated as a short circuit. So although I confess I'm not explaining it very well at this point, and part of it is because we haven't studied capacitors in depth yet. What we can do with this, and what I can tell you that how this circuit works, is that this capacitor is going to be an open for DC signals, and it's going to be a short for AC signals. And the reason I can say short is because if we accept that this capacitor is practically infinite, then anything that's not purely DC will result in that capacitor appearing like a short. And so the nice thing is what we get is for the DC or operating point, we end up having a circuit that is just the two resistors and RD. Okay, and so from here we have the basically V. This is V capital GS. Okay, and this is not a function of VI. So if VI has an offset voltage on it of 10 volts or 2 volts, whatever, it's not going to affect VGS because under static conditions, DC conditions, the capacitor isn't open. But under AC conditions, when the input signal is varying, what we end up having then is that the source connects right to it, right to the gate. And although we have R2 and R1 connected still, they do not affect the voltage at all. So here, R1 and R2 do not affect VGS, and this is the small signal VGS now that would be supplied by our VI. And the advantage of this scenario is that the voltage gain, sorry for the crowdedness here, but VO small signal over VI small signal is now equal to just the minus RD GM. In other words, no longer do we have the R2 or R1 over R1 plus R2 attenuation or term that we had back up right here. Okay, so we don't have that term anymore, and of course that term reduced the voltage gain of this amplifier a bit. Now, what's the drawback of this type of setup? The drawback is that now this is an AC amplifier only. If you were to put in a DC voltage at VI, the amplifier would not amplify it, because if you simply had a DC voltage at VI, at some point that capacitor will finish being charged and no more current will flow, and so the circuit to the right of the capacitor will no longer have any visibility to whatever DC voltage you're applying on the left from VI. So this leads to an AC coupled amplifier. Okay, AC coupled amplifier, i.e. rejects DC. So for things like an audio amplifier where you're just trying to amplify, say, 20 hertz to 20 kilohertz, you don't want to pass DC. So this is quite ideal. But in some applications where you do need to amplify DC, then putting this capacitor here would not be a solution to helping you with the biasing.